Okay, now I want to also refresh your memory on some other results that we have done. So, this is going to be a quick review with a very specific purpose, and hopefully this is going to be the building block for some of the things that we are going to be discussing today. So, if you remember, we wrote about a block which had the following notation. It was a parallel to serial converter of size m. Okay. Now, do you remember how this was done, parallel to serial conversion? Do you recall? Again, basically it was a downsampler, okay, by m, that was the top branch, and then we passed it through an advance operator, right, because we want if x0 is on the first branch, we want x of 1 on the other branch, which means that it must have passed through an advance operator, downsample by a factor of m dot 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 last advance operator, and then you passed it through a downsample by a factor of m. So, this was the serial to did I do that wrong? It is this is a serial to parallel converter. I am sorry. This is not parallel to serial. This is a serial to parallel converter. Okay. Yes, and then we also had another block which was the parallel to serial converter. So, to which you would feed in multiple blocks. So, this would have multiple blocks. This is output number 0, this would be output number m minus 1. So, likewise you have the input number 0, input number m minus 1. This is a parallel to serial converter also of dimension m, and this one we said had the following structure, where you would have the upsampler. In order to get the sequencing correct, you would have upsamplers in each of these branches, but these would be combined using a delay. If you remember, that was the, of course you can do parallel to serial to parallel conversion using a delay operation, but then the data samples will get swapped around. So, basically this is the structure that we have, okay, upsample by m, going through a chain of delays and then getting combined. Okay. So, I will just put dot dot dot, this is a adder, all of these are adding nodes. Okay. So, that was the parallel to serial conversion. Okay. Now, there was a result that we wrote down, if you remember, which was sort of seemed like a somewhat of a trivial result. The result was, if I have a serial to parallel converter of dimension m, that means I will get these parallel lines, and then I pass this through a parallel I should do the other way, I am sorry. I need to do the parallel to serial converter. The parallel to serial converter. Okay. I have many of these parallel to serial converter, and then followed by a serial to parallel converter, and if these are denoted as x naught of n all the way to x m minus 1 of n, and the outputs are denoted as y naught of n to y m minus 1 of n, this was trivially mapped in the following way. It was all parallel lines with a gain of 1. Okay. So, this was the x naught of n, x1 of n, xm minus 1 of n mapping to the output. So, basically there was nothing happening in the processing, the input got translated to the output, and this was seemed like a very trivial type of result. Okay. Now, can we revisit this problem, because that is what is going to be interesting to us. When we actually did the representation of the serial to parallel and the parallel to serial, we did not really study any applications. The applications are now coming in here. Now, keep this structure in mind, basically how the signal is combined in a parallel to serial converter and the serial to parallel. Now, if I introduced a delay of 2 units of time, z minus 2, okay, can you help me map what these input output relationships are going to be. So, basically there are m inputs exactly like before, okay, and there are m outputs, not clear that they will be just a straight mapping like before. Let us just visualize it. There is a branch, so take the upper branch, the topmost stream. The uppermost stream goes through a upsampling by a factor of m, then hits this delay z power minus 2, and then comes to the branch on the outside with the downsampling by a factor of m. That will be 0, because that we know, because if there is any non-zero delay between the upsampler and the downsampler, that will get killed. So, will this signal ever have a chance of coming to the output? Let us see if it will come through the any of the other branches. If it comes to the next branch, it is upsampled by a factor of m, there is a delay z power minus 2, and then the next branch has got z. That means overall transfer function is z power minus 1 will get killed. But if you drop down one more channel, z power minus 2 in the channel, z squared in the chain will come out. So, actually the x naught of n actually comes out on a different branch. It comes out on this branch. Okay. So, this is x naught of n, x naught of n, y2 of n is equal to x naught of n. Okay. So, and you can easily verify that the x1 of n will come out through y3 and so on until we hit x of m minus 2. Okay. The last one is x of m minus 2. Okay. Now, x of m minus 2 means that it was the last but one branch, it has got m minus 2 delays in the chain that it will go through the channel. What did it get? Another 2 units of delay. So, it got z power minus m as the now which of these branches will it come out through? The first one, because z power minus m is allowed, that means non-zero, but when I do the downsampling I will get 1 unit of delay. So, this one will be y, sorry I will use the red color, this one will be y0 of n is actually equal to x of m minus 2, do not forget the delay, there is an n minus 1. So, basically there is a connection between this one and this, but we have to mark a delay on that branch, okay, when you simplify. And similarly you can verify that the last branch also comes out with a delay. Okay. So, y1 of n is equal to x of m minus 1 n minus 1. So, a very interesting thing happened, it kind of took a cyclic shift, all of them sort of got a cyclic shift, but when they came back up those 2 branches had a delay element to it. Okay, so this is something for you to keep in mind, because we are going to build on this concept, and just as we use this concept earlier and we will come back to use it in today's class, we also had another concept that we have leveraged. I would like to use it for today's discussion as well. Okay, so the other one was polyphase decomposition. Polyphase decomposition. Remember, there were two types of polyphase decomposition, and almost very rarely we came across any application of the type 2 decomposition. So let me just refresh your memory on that, because today we will be using the type 2. Summation k equal to 0 to m minus 1 z power minus k e k z power m. This is type 1. Type 2 is summation k equal to 0 to m minus 1 z power minus m minus 1 minus k r k z power m. This is type 2. Now, one observation that we did not emphasize earlier, because it was not necessarily the time for it, is to simplify this one. Take this z power m minus 1 outside the summation. What will it become? Z power minus m minus 1 summation k equal to 0 to m minus 1 z power plus k, there is minus of minus, z power plus k r k z power m. So, this is type 2 also. Basically, I just have simplified that. So, actually another, if you take one more step, you take this z power minus 1 to the other side, then what we get is z power m plus 1, z power m minus 1, not plus 1, z power m minus 1 times h naught of z is equal to summation k equal to 0 to m minus 1. This is z power k, z power k r k z power m. Okay, I am just nothing clever or tricky here, just basically rewrote the type 2 polyphase decomposition. Okay, now for a very specific reason. This looks like a non-causal representation. It is actually not non-causal, it is strictly basically what we did was, you took a filter H naught, you kind of shifted it and rewrote it so that you get this representation. Now, why did we even take the effort to do this? Primarily, if you want to go back and look at this structure, if you want polyphase components which have a structure without delays, but see, otherwise what you would do is you would end up with only the type 1, all of them will have delay. So, if I want a structure where there is the provision for me to move the downsampler around, but I want to have powers of z, right, delay, advanced elements, then that is why, so anything which requires this type of a representation, we will actually utilize the type 2 polyphase decomposition. So, again keep that picture in your mind. We will come back to link it to the, when we need it in a short while we will do that.